It's time to learn some more equilibrium. Welcome back to AP Chemistry. In this video, we're learning about some applications of equilibrium and what happens if you mess with or disturb a system at equilibrium. Now, we learned in the last series of videos that equilibrium is a state that you have when the concentration of a system has basically stopped changing. So it doesn't mean the reaction has stopped. It just means that the forward rate is the same as the reverse rate in a chemical reaction, in a reversible reaction. But what happens when you disturb that system? Well, there's a principle that helps us to answer that. It's called Le Chatelier's principle. And it essentially says that when you have a system at equilibrium and you disturb that equilibrium, the system is going to shift to counteract that disturbance and return to equilibrium. Now, what does that mean? Well, to illustrate this, let's go back to the dance floor problem that we had back in the previous lesson, back in our previous series of videos. So let's take a look at the dance floor problem, and this is where we left off. If you want to see how we got to this point, I'll post a link in here so that you can see how we got to this point. But we have a dance where there are 300 people total, and there are 181 that are not dancing, and there are 119 that are dancing. And we find that after every song, 30% of the people that are dancing sit down, and then 20% of the people who are not dancing get up and start dancing. So we found that we had a net of 36 going in each direction, 36 in each direction. Well, let's disturb this dance floor equilibrium. We're going to have some party crashers. And so we're going to put 30 party crashers that show up at the party. And so instead of having 300 people at the dance, we now have 330 people there. So we now have 211 people that are not dancing. We still have 119 that are. Well, let's go back to the math here. We know that 30% of that 119 are going to sit down, which is still 36, but 20% of the 211 are going to get up and start dancing. So I think that's 42. Yes, so now we're kind of back where we were earlier in this example, where we're going to have a net change of, looks like positive 6 in the direction of the dance floor. So this side goes up by 6 to 125. This side goes down to 205. And we can do this again here. 30% of the 125, that's 38, I believe. And 20% of 205 is 41. So we have a net change of positive 3 in the direction of the dance floor. So we'll have 128. This side goes down to 202. Do the same thing. 30% of 128 is 38. And then 20% of 202 is 40. So that's a net change of plus 2 in the direction of the dance floor. So it's 130 and 200. Now 30% of 130 is 39. And 20% of 200 is 40. So we have a net change of positive 1 in the direction of the dance floor. So it's 131, 199. Do it again. 30% of 131 is 39, and 20% of 199 is 40, so it's positive 1 toward the dance floor, so it's 132, 198. Do it again. 30% of 132 is 40, and 20% of 198 is 40. So look at that. We're now at the same position where we have the same change. The net change is 0. So guess what? For the next song, it's a 132 and 198. And we could keep doing this, multiply it out. It's 40 in each direction. So the numbers don't change. So we had the party crashers, but we returned to dance floor equilibrium. It took a few songs, didn't it? But eventually we got back to dance floor equilibrium. Now let's analyze what we just did here. What was the eventual effect of throwing an additional 30 people onto the not dancing side? What was the net result? Well, as you notice, it actually caused the other side to increase. See, it went from 119, but it actually went up. And the side that we added the dancers, or the party crashers to, I should say, because they weren't all dancing, the side I added the party crashers to actually went down as time went on. Now, the same thing happens when we add substances in a chemical reaction. Whenever we have a chemical reaction and we add a substance, it's going to cause an increase to the other side of the reaction. So that means, for example, if we have this chemical reaction and it's at equilibrium, let's say, if we decide to toss in some CH4, some methane, it's going to cause an increase in the amount of carbon disulfide and in hydrogen. Or as we sometimes say, it shifts the equilibrium to the right, in this direction, to the right, or to the product side. Likewise, if we add some, let's say we add some carbon disulfide, some CS2 or some hydrogen, well, it's going to cause an increase in the other side of the reaction, right? Going to go in this other direction here, to the left. So we're going to have an increase in the hydrogen sulfide and in the methane, CH4. And when you add hydrogen, the same thing, it goes to the left, right? When you add something, it causes the other side to increase. Well, guess what? The opposite is true as well. If you take away a substance, it causes an increase on the same side of the reaction. So that means if I were to remove the methane, take away some CH4 if it's at equilibrium, it's going to cause the equilibrium to shift back to the left. So that means that we're going to make some more methane and some more hydrogen sulfide. And we could say the same thing for the other side. If we take away carbon disulfide or take away hydrogen, we're going to shift the equilibrium to the right, right? And we're going to make more carbon disulfide and more hydrogen. And it's going to cause a decrease in the amount of H2S and CH4. Okay, so that's how it works. So if you add some other things, let's say that we add some other inert gas. So maybe helium or argon or some other gas that doesn't react with any of those four things, it's going to have no effect on equilibrium. So sometimes they throw that question in there just to trick you to see if you know what's going on. But if you add some inert or some noble gas, the answer is it has no effect on equilibrium. Now, how about adding a catalyst? Well, we'll talk about kinetics and what a catalyst does later on in this course. It speeds up a reaction, but it has no effect on equilibrium. So those are some two things that they sometimes throw in as like a little trick question to see if you know what's going on. But those two things, inert gases and catalysts, have no effect whatsoever on equilibrium. So let's practice. Here we have a methane, not methane, this is octane actually, isn't it? And it's liquid, so the liquid doesn't really affect equilibrium, but it is reacting with 25 moles of oxygen gas, and it's making 16 moles of carbon dioxide gas and 18 moles of water vapor. So what's going to happen to the concentration of carbon dioxide? So that's, that is this stuff right here. If each of the following changes is made when the system is at equilibrium. So let's start by adding some oxygen gas to the reaction mixture. Well, if you add the oxygen, it's going to shift equilibrium to the right, isn't it? We're going to have more products. We're going to have more carbon dioxide. We're going to have more water vapor as well. So the CO2 is going to increase, isn't it? So that's the answer for that one. How about water vapor is added to the reaction mixture? So we're going to add some of this stuff here. Well, when you add something, it shifts it to the other side. So we're going to make some more of the other side. So we're going to shift it and make the reactants. So that means oxygen should go up, and that's going to happen at the expense of carbon dioxide and water. So CO2 will go down. It will decrease. How about adding some octane to the reaction mixture? Well, octane, C8H18, is a liquid, isn't it? And so does that even affect equilibrium? It does not. And so we're going to answer that there is no effect. Whoops, that's wrong. So we're going to mark that out, and we're going to say that since octane is a liquid, there is no effect. Remember, liquids and solids have no effect on equilibrium. How about water vapor is removed from the reaction mixture? So we're going to take some of the product away. So that means if we remove a product, we shift the equilibrium to the right some more, don't we? So we're going to make more carbon dioxide and more water. So CO2 is going to go up. It's going to increase. How about oxygen gas is removed from the reaction mixture? Well, if we take away a reactant, it goes in the direction of that side. So we're going to make more oxygen, and that's at the expense of CO2 and water. So carbon dioxide is going to go down in that case. How about some argon gas is added to the reaction vessel? Well, that's an inert gas. Argon has nothing to do with this reaction, does it? So the answer is no effect, no change. Now, we can add things, we can take things away, but what about changing the pressure? Now, the easiest way to change the pressure in a reaction vessel at equilibrium is to change the volume. We can maybe have, perhaps the system has a piston on there. We can make it smaller. We can release the piston, make it larger. So that's the way to change the pressure, changing the volume. So here we have this chemical reaction that we looked at earlier. Well, if we increase the pressure, that means we decrease the volume, we compress it down, it's going to shift equilibrium toward the side that has fewer moles of gas. So if we look at the coefficients here, we have a 1 right here, and there's a 2 here. So there are 3 moles of gas on the reactant side, and there's 1 versus 4. So that's 5 moles of gas on the product side. So if you decrease the volume, we are going to shift it, in this case, to the left. We're actually going to make more methane and more hydrogen sulfide. We're going to have less carbon disulfide and hydrogen. It kind of reminds me of when you move into a place that's very, very small, like a college dormitory room. You have a very small amount of room most of the time, and so as a result, what happens? Well, you have to get rid of things, or you have to thrive with fewer belongings or fewer possessions. And so guess what? When this reaction has to move into a smaller space, it thrives in a system where you have fewer molecules as well. So it shifts that equilibrium, in this case, to the left because there are fewer moles of gas. Now, the opposite is true as well. If you decrease the pressure, you increase the volume, it's going to shift equilibrium toward the side that has more moles of gas because that's going to take up more space. It's like after you graduate college and you decide to buy a house, all of a sudden you have all this room, and guess what? You probably are going to acquire more possessions and have all kinds of space for things. So when you have more space, it's going to tend to be more stable with more possessions. So when this reaction here moves into a larger space, it's going to move toward the side that has more moles of gas, more possessions. So that's going to be the right side in this case, the 5 moles. So let's do some practice here. We have a different reaction. This is one we looked at earlier. What's going to happen to the concentration of carbon dioxide, that stuff right there, if we do each of the changes? So let's increase the pressure. So once again, we're increasing the pressure. That means we're decreasing the volume. And so it's going to tend to go toward the side that takes up less room, right? That has fewer moles of gas. So on the left, we have, let's see here, we have 25 moles of gas because that liquid doesn't count. And on the right side, we have 16 plus 18, so I think that's 34 moles of gas. So it's going to tend to go toward the left side, isn't it? Because that side takes up less room. So if it goes to the left, that means that the carbon dioxide is going to decrease because that oxygen is being made at the expense of carbon dioxide and water. What if the pressure is decreased? Well, that means the volume is increasing, and it's going to tend to go toward the side that has more moles of gas because that takes up more room. So that's the product side. So we're going to make more carbon dioxide and water. So that CO2 is going to increase as it shifts that equilibrium to the right in this case. Now, there's one other thing we can do. We can change the temperature. Now, as it turns out, all these other things we've talked about, adding things, adding substances, taking them away, changing the pressure by changing the volume, those things do not change the equilibrium constant's numerical value. The only way you can actually change the numerical value of Kc or Kp or any equilibrium constant is by changing the temperature. Now, let's say we have this reaction. Now, as you can see, that is an exothermic reaction, very exothermic. In fact, it gives off a lot of kilojoules. Now, it doesn't matter what the number is, but since it's exothermic, that means that heat is a product. And so I'm actually going to write that in here just so that we can see that. So I'm going to put plus heat as a product here because, if it's exothermic, heat is a product. That means that when you raise the temperature, you're adding heat, aren't you? So when you add heat, it's like adding any other product. It's going to send equilibrium toward the other direction. So we're going to make more oxygen at the expense of carbon dioxide and the water vapor here. So in this case, raising the temperature sends the equilibrium to the left. Well, guess what? If we lower the temperature, that means we're removing heat, aren't we? So that's just like removing any other product in this case. So if we were to remove the heat, we're going to make more carbon dioxide and make more water vapor at the expense of the reactants. So, of course, if it were endothermic, heat's a reactant, so it goes the other way around. Let's try this example here. Here we have another reaction that we've looked at before. It is endothermic, as you can see. So that means that heat is a reactant. I'm going to write that down here, that heat is a reactant. And so what's going to happen if we increase the temperature? Well, if we increase the temperature, we're adding heat. And so that's like adding any other reactant in this case. So we add heat by raising the temperature. It's going to shift equilibrium to the right in this direction. So that means we're going to make more carbon disulfide and make more hydrogen, right? So CS2 is going to increase, and the methane and the H2S are going to decrease, aren't they? And of course, what if we decrease the temperature? Well, then, of course, the opposite happens. We're taking away heat, so that means we're going to shift the equilibrium back to the left. So we're going to make more methane and make more hydrogen sulfide, and the carbon disulfide and hydrogen will go down. Okay, so that's how it works. How about a multiple choice question? Which of the following changes is going to cause the actual equilibrium constant in that reaction to increase? Well, there are a couple things we can already rule out. The only way to change the equilibrium constant is to change the temperature. So I'm going to eliminate choices A and B automatically because, those won't do anything to the constant. So which is it? Raising the temperature or lowering the temperature? Well, let's think about it here. If you want the equilibrium constant to go up, the equilibrium constant is always written as products over reactants, isn't it? Raised to the power of the coefficients. And so if I were to write, the equilibrium constant for this reaction, Kc, it's going to look something like this. All over CH4 and then H2S squared. So if I want to increase the actual value of that equilibrium constant, then I want to increase the CS2 and the H2, right? Because that's going to make the number go up and make that value go up, okay? So how can I cause the CS2 and the H2 to go up while making the CH4 and the H2S go down? Well, I have to shift the equilibrium in this direction. And so that means I have to add heat, right? So that means I have to increase the temperature. So raising the temperature is how that's going to work. So hopefully you can use your math skills and what you know about equilibrium constants to answer these questions. Hope you enjoyed the video. Hope you learned something about Le Chatelier's principle. I know this was kind of a long video, but there is a lot going on here as we look at these. If you enjoyed the video, please give me a thumbs up if you'd be so kind as to do so. That way YouTube will share my video with other chemistry students. Join me again. I hope you continue your successes in chemistry. I've been teaching AP Chemistry for over 20 years, and I want to share my knowledge with you. So join me again where we can continue our journey through chemistry and learn some more chemistry together.